Thank you. First of all, I'd like to thank organizers, first of all, for organization of this event to memorize my great teacher, Anatoly Moiseevich, and also for invitation to give a talk. I regret that I cannot be offline with you, unfortunately, but I hope that I can talk a bit. This morning, when I wake up, a social network suggested me several photos to remember, and I find it is a nice coincidence that some of them were photos of Anatoly Moiseevich, and possibly this means that I should share them. Let me try. Can you see Anatoly Moiseevich?
Yes.
Yes. Yeah, great. So let me show a couple more, and then I switch to the talk. These are photos of November 2007. Okay. Well, I think that's the two are enough. Others are similar. What I am speaking about is our joint work with Danila Cherkashin, and a couple of days before Anatoly Moiseevich passed away, we discussed what I can speak about at his seminar, and this was one of suggestions. Unfortunately, it was not realized. So I consider this talk as some substitute of this talk at our seminar. The topic relies two subjects which both are quite different. One of them is optimal transportation. Okay. I don't understand what happens. Yesterday it works nice. Well, so well, what is it about? That we have two measures, mu and nu, probability measures on the same space. And we want to transport mu to nu. And it costs, it is not for free. And for example, if they are on the metric space, x, x, d, then, for example, transporting 1 gram per 1 meter costs €1. So well, let me think what can I do. Well, and the problem to solve is to minimize total cost. Gram, it means that in terms of measure, that measure is a distribution of mass. Minimize total cost. Yeah, so it's impossible. Let me try 1 minute to replace the tablet to another one. I'm sorry. Well, let me proceed.
Okay.
So, for example, yes? Yeah. For example, if both measures have finite support, assuming for simplicity, that we represent the difference as a linear combination of differences of delta measures, and we minimize sum of this cxy times distance between x and y. That the core holds in the metric space xd. Okay, but that's a classical optimal transportation problem for which Leonid Vitalyevich Kantorovich, the beloved teacher of Anatoly Moiseevich, is especially famous for. And this quantity is called the Kantorovich distance between measures mu and nu. There is a tradition to call it Wasserstein distance, and Anatoly Moiseevich was a big fighter for Kantorovich priority in this question. Well, but what we consider is a slightly different optimal transportation problem. It concerns the problem with branching. For example, imagine that we have measures on the plane. Say we have some mass here and mass here, and want to transport it here. And we are allowed to use extra points. For example, we may move all these measures to this point, and after that, it goes here. Also, let's assume that moving m grams per distance d costs m to the d. Not m to the d, it would be too much. M to p, where p is between 0 and 1. So, for example, if you have 2 kilograms of goods and you move them to distance d, it is better than twice move 1 kilogram. That is quite reasonable. Okay. Then we may define so-called flow. It means the following, that we represent our measure, mu minus nu, as a linear combination of say, let us call it m xy times delta x minus delta y. And we let us suppose such a formalism that m of xy equals always minus m of yx. And here the sum is over a finite set of points. Let us call them edges. And the cost is such a functional sum cost of mxy let it cost be defined on positive number, so let it be absolute value times distance of xy. And so the cost which we consider, first of all, is m to the p, where p is between 0 and 1, and this is called Gilbert, for Edgar Gilbert, or Gilbert, I don't know how to, Gilbert Steiner problem. Okay. And actually, as I said, the branching is possible. So it is possible that it is better to use this extra point, which was not known in advance, and it costs less than if we don't use branching points. And the result which we prove, and which I want to discuss, is the following theorem, that in optimal branching transportation on the plane, there are no branching of degree in graph theoretic sense more than 3. The previous result proved by Liebman, San Martin, and Humphrecht is that the same, but with degree greater than 4. So we excluded the branching of degree 4. And degree 3 may exist, so in this sense, that is the final answer. And it is quite unexpected that, at least it was for me, that the proof of this result uses the theory of positive definite functions.
So does it mean that if you have, for instance, 4 masses, different masses, so they glue in one?
Yeah, for example, yeah, if I have 4 masses, such is not optimal. Such transportation. It is always worse than transportation with all branching only of degree 3. Yeah, okay. Well, so I recall that positive definite functions are such functions that f, that the matrix f of xi minus xj, where ij, I don't know, from 0 to infinity, has all minors non-negative, or where xi and xj are arbitrary reals. This is a function of a real variable. We need slightly different question. This is the subject of the theorem of Bochner. That these functions are Fourier transforms of non-negative meshes. And we consider slightly different question when this function xy to f of x minus y metric on R, which can be embedded to Gilbert space. Well, let me now tell the answer. Actually, we use the so-called easier part of the theorem, which says that for some functions, yes, this is subject of a paper of Schoenberg. Of course, this embedding to Gilbert space is given to x to e to I to x in L2 with respect to submeasure lambda, because the distance between these two functions, I to tx minus e to isx, equals to the distance of e to I t minus s x minus 1, right? It depends only on t minus s. Okay, but actually not quite, because we need a measure for which this is not square summable, and this is resolved by subtracting 1 here. If you subtract 1, this function becomes 0 at point 0, and so it is integrable over more measures. Exactly what we need is the function x to p. X to p. Well, maybe not x, but t to p. It is some constant times p times norm of e to x minus 1 in L2 with weight t to 2 pi minus 1, if I am not minus 2p minus 1. So minus 1 is also the exponent, of course. Let's see. It is one-line computation, yeah, because we need such an integral of e to 2x minus 1 square t to minus 2p minus 1. So it is x. Yeah, because t is parameter, t defines a function. X to 2 minus p minus 1 dx. First of all, this integral is convergent, yes, because at 0, this behaves like x squared, and 2 minus 2p minus 1 is greater than minus 1. So the exponent is such that this is summable. And to compute this integral, we simply denote x equal to tx equal to nu lambda tau. Yeah, so x equals to t2 minus 1 times tau, x to minus 2p equals 2 to 2p times tau to minus 2p. This is out of integral, and the rest of integral doesn't depend on t. Yes, so it is some constant. It is denoted cp square times t to p. As we maybe okay, -2 doesn't matter. Well, okay, so what I need that this function t to the p, which is used for measuring the cost of transportation of mass, is proportional to is proportional to the norm of such function in L2. And how is this so related to our branch transportation? Let's see. First of all, we use the following very simple idea. Assume that we have a branching point. For example, this is all UV. Let us try to improve it by introducing new point here. Yeah, and yeah, so there was mass mu. Here was mass mv going from here to here. This masses may be negative, so it means that in generalized states in the center flow. Yeah. Then for new point, we have mu here, mv here mu plus mv, right? So let it be a new point, call it T. Well, we consider taking the derivative, which I miss here. We see the following condition: that note that we have piece powers of all these guys, so mu to the p, mv to the p, and mu plus mv to the p. These are costs. And since p is less than 1, we know that they are the sides of a triangle. Let us denote it ABC. This is C. And let this angle be beta, this angle be alpha. And assume that angle UOV is less than alpha plus beta. Then we may move in such direction, then this is less than alpha, and this is less than beta. It is not hard to see that in this case, moving O to T decreases your total cost. And if our transport is optimal, then this doesn't happen. We cannot improve it. And therefore, we have that angle UOV is at least alpha plus beta, which is pi minus this angle gamma, yes? Okay. So now we can discuss why we cannot have a branching of degree greater than 3. For example, we have such a branching. Let us denote these masses by M1, M2, M3, M4, and so on, Mn. And n is greater than 3. Then let us collect all such triangles. We have this condition for every of these n angles. And let's, but these triangles ABC, they are always different. So let's see that actually they correspond to the same points. So consider such a point, AJ equal to E by M1 plus MJ X minus 1 in L2 of x to P minus 1 dx. Yeah, so this is Gilbert space. We consider this point and this. And note that, as we discussed, the distance between AJ and, for example, AJ minus 1 is some constant. I don't remember CP or CP2 inverse, it doesn't matter. Some constant times mg to p, right? And aj plus 1 minus aj minus 1 is the same constant times mj plus mj plus 1, again, to power p. Yes, that's how we constructed this exponential. Okay, so this triangle with such side lengths is a triangle AJ, AJ minus 1, AJ, AJ plus 1 if we are in this triangle here. So if we denote these angles phi1, phi2, and so on, phi(n), then we get that phi(n) is greater on or equal to pi minus angle AJ, AJ minus 1, AJ, AJ plus 1. P pi j. Right? So we have such an equality for this broken line in Gilbert space. Well, we are almost done. Because if you have a broken line in a Gilbert space, like I draw on the plane, but then the sum of these angles is always at least 2 pi. And if the points are not planar, so if we are not in the same place, that it is strictly greater than 2 pi. This is an elementary geometric inequality. Yeah, that sum of a cyclic sum, j from 1 to n, p minus angle aj minus 1, aj plus 1, is at least 2 pi and strictly greater if not planar. This fact has a one-line proof also. We may consider the random direction u. Direction is a point on the sphere of corresponding dimension. Of course, when I say Gilbert space, but they of course lie in the finite dimensional subspace, so it is understandable what is random. So we get a random direction and consider such an event. Then the point AJ is the highest. The highest if this direction is called vertical up, the U highest. Of course, the sum of probabilities equals 1. Oh, okay, it is at least 1, but usually it equals, because usually we have exactly one highest point, yes. But this sum of probabilities is at least this sum of probability that AJ is higher than AJ minus 1 and AJ plus 1. This is tautological, right? And this very probability, it means that it exactly equals to this guy divided by 2 pi. So it is sum of pi minus angle AJ minus 1, AJ plus 1 divided by 2 pi. Simply because this is if you draw a picture, it is a diagonal angle, yes, at this point. These 2 points must be both below that point. It is this direction with such angle, which has this measure. Okay, for that, I think it means that this sum, sorry, this is at most, yeah. Yeah, that's now correct chain of inequalities. And it is easy to see that if they are not coplanar, that it is strictly because these events are not equivalent to these events. Okay. So they must become planar, and this because these exponentials are linearly independent. That may be seen from their Taylor expansion at 0 or anyhow else. It is easy in this situation. So they are linearly independent. It means that these points have only 3 different values, but it cannot correspond to such a believe me that it is to see that all inequalities cannot simultaneously turn into equalities in this case. Yeah, so I think we proved this result. And a couple of extra words.
Maybe quick,
yes.
because
Yes, I understand, yes. A couple of words, it means about 1 minute, yeah. In 3-dimensional case, branching of degree 4 is possible. Also, for functions which are not positive definite in Schoenberg sense, also branching of degree 4 is possible. And this is quite remarkable in a sense, because for Steiner problem, which you minimize the tree which connects the given collection of points, branching of degree greater than 3 is not possible in no direction. For example, in tetrahedra, such tree is never optimal in 3D. While for the planar case, everybody knows, yes, that you should have Torricelli point with equal angles here. Yeah, but in this situation, branching degree 4 is possible, and we know, I think, nothing more. We don't know which degree is possible and in which dimension, how to bound it. So apart of this planar result, it remains widely open. So thank you very much.